If you fell into Jupiter, you'd never hit a solid surface. Your descent would be an endless plunge through violently churning clouds into absolute darkness. About 1,000 kilometers down, the environment undergoes a radical shift. The temperature skyrockets to thousands of degrees, and the atmospheric pressure climbs to crushing levels. The gas completely vanishes. Calling Jupiter a gas giant is a misunderstanding. A spacecraft dropping into the planet wouldn't splash into a defined ocean. It would simply sink as the atmosphere seamlessly thickens around it. Thousands of kilometers deeper, the pressure reaches 1 million times that of Earth's atmosphere at sea level. At this depth, the chemical bonds holding diatomic hydrogen molecules together are crushed. The molecules break apart and their electrons are stripped away. With its electrons freely flowing, the hydrogen transforms into a highly conductive fluid known as liquid metallic hydrogen, burning at 6,000 Kelvin. Because of this phase shift, the vast majority of Jupiter's interior actually consists of a colossal, churning ocean of liquid metal. Jupiter completes a full rotation every 10 hours. That rapid spin violently churns the conductive metallic ocean, creating a massive planetary dynamo, a rotating electrical generator. Measurements from NASA's Juno spacecraft confirmed this internal generator produces a magnetic field 10 times stronger than Earth's. This 3D model maps the structure of that magnetic field. Instead of a symmetrical dipole, the magnetic flux lines are irregular and lumpy. Near the equator, the data reveals an isolated magnetic bulge known as the Great Blue Spot, actively shared apart by planetary winds. To explain these magnetic anomalies, researchers theorize Jupiter houses a stably stratified fluid layer deep inside, a distinct zone where internal fluids resist mixing. The interaction of this metallic ocean, the unmixed fluid layers, and the rapid spin turns the planet into the most powerful electrical engine in the solar system. Higher up in the atmosphere, the extreme conditions drive severe chemical weather. Violent lightning strikes tear methane gas apart, leaving behind raw carbon soot. As that soot sinks into the deeper, higher pressure regions of the planet, the carbon atoms are squeezed together to form solid diamonds. We know this process works because researchers have recreated icy giant conditions here on Earth at the LINAC Coherent Light Source Facility in California. By firing high-powered X-ray lasers into plastics, scientists generated shockwaves that mimicked extreme planetary pressures. This allowed them to watch carbon atoms clump into solid nanodiamonds in real time. Millions of carats of these diamonds fall as dense precipitation deep inside Jupiter. As they sink, they generate friction and release heat, providing a direct internal energy source that helps fuel the churning metallic ocean. Jupiter defies the traditional definition of a gas giant. It operates as a rapidly spinning ocean of liquid metal, powering a colossal magnetic field. Human engineering can only maintain these extreme states of matter for a few femtoseconds in a laboratory. Jupiter has maintained them continuously for billions of years. Juno's gravity measurements also resolved the structure of the planet's center. Rather than a dense, solid sphere of rock and ice, Jupiter contains a dilute core, where heavy elements are thoroughly mingled with the metallic hydrogen. This fuzzy, dilute region extends up to halfway through the planet's radius, entirely discarding traditional three-layer models of planetary structure. Charting this internal structure provides the exact baseline required to decode the physics of giant planets in other solar systems. The largest planet in our solar neighborhood operates as an active laboratory of extreme physics, challenging our models of how planets form and evolve.